So I think it's fair to say we've probably found this entropy test a lot trickier than the last couple of assignments we've done, and there were some quite difficult questions there. Unfortunately, that's just the reality of A2 chemistry. Sometimes you get questions that are quite straightforward and just out of the notes. Sometimes you get ones you have to apply your knowledge a lot more, and we put a couple more of those type of questions in this test. But in this video, I'm going to go through each question in turn and explain each answer. So obviously, skip forward the bits you got wrong, and hopefully this will make it a wee bit clearer how you could approach those questions. So first one gives you a table of information about some substances, gives you their enthalpy of formation data and their standard entropy data. First part of the question, calculate the standard enthalpy change for the reaction of extracting iron. So it gives you an equation, gives you the data, so you have to work out the enthalpy change of the reaction. So this in fact is a Hess's law question, because you have to find an alternative route for working out the energy change there. Whilst obviously that's not strictly speaking in this 4.2 topic, something you'll find a feature of A2 chemistry is they'll bring in wee bits and pieces from AS. You won't get a whole question on it, but you will get a wee question like this from AS stuff. So in terms of approaching it, so I always like doing the cycle out in full. So it's iron oxide reacting with 3 carbon monoxides to make 2 irons and 3 carbon dioxides. In terms of the data I've got on the table, I've got enthalpy of formation data. So that's going from elements to compounds. So I'm going to put elements at the bottom of the cycle. And we're going to go up to the compounds from there. Transferring my data across, so I need a value for iron oxide, that's minus 824.2. Value for carbon monoxide first, 3 times minus 110.5. Value for iron, remember it's an element, so you can't form an element from an element, so it's just 0. And last bit, 3 carbon dioxides, 3 times minus 393.5. So Hess's law says that it doesn't matter what route I take for the reaction, the enthalpy changes will be the same. So I need an alternative route going from left to right, so it's going to involve going down first, then up. So I need to change these arrows, so the arrows make sense. So if I change an arrow, I need to change the sign. So it's plus 824.2 and then 3 times plus 110.5. So my delta H for the reaction is therefore 824.2 plus 3 times 110.5, which is positive now, plus, following this arrow, 3 times a minus number 393.5 there. So I could, strictly speaking, chuck that on my calculator just like that, but what I'm going to do is just split it up. So the first bracket for the reactants is 1155.7. For the products, it comes out as being minus 1180.5. The final answer, therefore, is minus 248 kilojoules per mole. A few of us dropped the minus sign and our answer was cost us a mark there. Just be careful of that. So that's part A. Part B is calculate the standard entropy change for this reaction. That's a normal kind of question in this topic, calculating entropy change. It's still the same reaction, but the expression we use here is a little bit simpler. It's just delta S, the change in entropy, is the entropy of the products minus the entropy of the reactants. So just need to use my table to work those out. So the entropy of the products first. So the first product is iron. It's going to be 2 times 27.3 plus 3 times carbon dioxide. It's going to be 3 times 213.6. Taking away the entropy of the reactants. So that's going to be 87.4 for iron oxide plus 3 times 197.6 for carbon monoxide. My two brackets are therefore 695.4 for the first bracket minus 680.2 for the second bracket. Comes out a final answer of positive 15.2 joules per Kelvin per mole, remembering the slightly unusual units for entropy. So moving on to the next question. So I'm asked to look at this next similar looking equation. So by equation between iron oxide and just carbon this time to make iron was carbon monoxide. They've given me the delta H value, they give me the delta S value, so that's law of the hard work done. What they've asked me here is to work out the temperature at which this reaction becomes feasible. So that's a standard question in this topic. There's a little section notes about it. It's called calculating the temperature feasibility. So the key thing I think about here is whenever we're talking about feasibility of reactions, we're always talking about delta G and whether it's positive or negative. Because remember, negative delta G is always favourable, positive delta G is always unfavourable. When it's asking you to calculate the temperature feasibility, it's asking you to find a bit where it's just at that tipping point becoming feasible or not feasible, so between positive and negative. what we say mathematically at that point is that delta G is 0. At that point, you're just about becoming feasible or just about stopping becoming feasible. So that's the bit we're looking for. So delta G is 0, and then we sort of derive the rest from there. So this needs the temperature for that, so you need T by itself, and a little bit of rearrangement gives you T equals delta H over delta S. And it's just a case of subbing those values in to get your temperature. One catch to that question, which call a few of us out, you have to be careful with your units. The units for enthalpy changes is normally kilojoules per mole, as written there. The units for entropy changes is normally joules per Kelvin per mole. Key thing is that units always have to match up in a calculation like this. The issue is with the joules term. Kilojoules per mole in the top, joules per Kelvin per mole in the bottom one. That's not consistent. We have them both being the same. You could technically change either, get them both either joules or kilojoules, but the standard kind of approach to this is to turn them both into kilojoules. So that will involve dividing your entropy value by 1000 to get it technically into the kilojoules per Kelvin per mole. So in terms of what this sum actually looks like then, it's going to be 492.7 on the top, divided by 542.6 over 1000. Remember, most calculators you can just chuck a fraction within a fraction without too much bother. And just hit equals, and then your temperature will come out as 908 Kelvin. So it's a standard question. Now, this next one isn't such a standard question though, so this is an example of where we're pushing out a wee bit and it's becoming a bit trickier. Calculate the temperature in which the standard free energy change is the same value of the reactions in part B and part C. So we've encountered two different reactions in this question so far. They've both involved iron oxide, but they're reacting with either carbon or carbon monoxide. So two different reactions. They both have their own bits of information, delta H and delta S, etc. What we've been asked to work out is at what temperature would their standard free energy change value, so delta G, be the same. So that's not out of the notes, it's applying your knowledge, it's beyond the spec, it's a tricky question. Here's how we approach it though. What I want to think about is what the equation for free energy is, which is delta G equals delta H minus T delta S. If I said that this was just for the first reaction, again, not saying which one it has to be, just maybe the first one at the top of the question, I'm going to call it delta G1, and that would be given by delta H1, so the enthalpy change for the first reaction, minus T delta S1 for the entropy change for the first reaction. I could do a similar expression for the second reaction, so delta G2 equals delta H2 minus T delta S2. The key sort of bit of the question to get towards the answer is realising if the standard free entropy change is the same at a particular temperature, which might be just by coincidence, the delta G values I can set equal to each other. So delta G1 for the first reaction will be identical to delta G2 for the second reaction. If these values are similar or the same, these values will be the same as well, so I can set them equal to each other. In other words, delta H1 minus T delta S1 will equal delta H2 minus T delta S2. And at this point, again, we were close to the answer. I'm asked to work out the temperature for which that's going to be true, that the delta G's are going to be equal to each other. So I need the T's by themselves. It's going to move this T delta S value over to join its neighbour over there, and I move this delta H value over the other side as well. So that becomes delta H1 minus delta H2 equals minus T delta S2 plus T delta S1. So at this point, make it a bit clear, I'm going to put the T's by themselves, so take them out. So it's going to be T upon delta S1 minus T, or minus S, minus delta S2. It's because delta S1 is the positive one, and delta S2 is the negative one, all times by T. And that's still equal to delta H1 minus delta H2. On T by itself, so I'm going to take that whole S term to the other side. T equals delta H1 minus delta H2 over delta S1 minus delta S2. So it doesn't actually matter in this case which reaction of the two ones you've got to look at you actually take first. The answer will actually come out the same because it's a fraction and the signs will cancel out. One important thing though is, again, that little pitfall with entropy versus enthalpy and your units. Again, we have to make sure your units are consistent. So I'm going to have to divide by 1000 these delta S values like I've done before. So subbing my terms in, so if I decide that the top reaction, or the reaction we encountered first in this question is reaction 1, we worked out its delta H value is minus 24.8, and the entropy or enthalpy change of the second reaction, the one in the previous part of the question, we calculated, or it was given to us as 492.7. It's going to subtract that because it was a positive value. The entropy changes, we calculated the first reaction is 15.2, it's going to do 15.2 over 1000. Taking away the entropy change of the second reaction, which is plus 542.6 over 1,000. At that point I could just type it onto my calculator in one step, or I could split it up. So if I split it up, on the top line it becomes minus 517.5. On the bottom it becomes minus 527.4 over 1,000. And that point in my calculator goes, and I get a final answer of 981 Kelvin. So tricky question, beyond spec. A few of us got it, which is really good. A few of us got it close, and a few of us got stuck. But that's how you would approach the question like that.